Implicit Differentiation, Part 1. Let's do a quick recap of some of the concepts and notation we've learned so far. The average rate of change is the slope between 2 points, so that gives us the slope of a secant line. So if we're looking at the slope of this line, we can see it's the slope between these 2 points. So that's the change in y, y2 minus y1, over the change in x, x2 minus x1, and that's equal to the slope of the secant line. One of the things we're interested in is what happens as x gets closer and closer to a. So as we move from whatever value this is for our input closer and closer to a. And as we observe this, we can see the slope of this line changing. So one thing that happens as x gets closer to a is that the distance between them, the change in x, delta x, approaches 0. So we have delta x approaches 0, but with that arrow to stand for that approaches. We also see that the slope of the secant line, which was started off like this, is the slope between 2 points. So this is my secant. Gets closer and closer to the slope of the tangent line. So right now, this blue line is the tangent line at the point a f of a. So what we can say is that the limit as x approaches 0 of the change in y over the change in x, so that's the average rate of change, approaches the slope of the tangent line. The instantaneous rate of change is the slope at one point. So this just goes through that one point. And that is a tangent line, so it's the slope of the tangent line. So the slope of the tangent line is equal to the limit as the change in x approaches 0 of the change in y over the change in x. And one notation that we'll use is with differentials. That's what these guys are called. So the limit as delta x approaches 0 of the change in y is equal to dy, and the limit as the change in x approaches 0 of the change in x is dx. Finding the instantaneous rate of change, so the slope of a tangent line, is one of the big concepts in calculus. And we're even able to find the instantaneous rate of change at almost any point on a function. So we don't have to find it for just one specific point. We can find something else that'll help us find all those slopes. This thing is called a derivative. So a derivative gives us the slope at any point of a function. And we denote it a couple different ways. So we can either say that the derivative is dy dx, so that's the derivative of y with respect to x, or we can call it f prime of x. And these are all equal to each other. So we can look at this definition, which shows us that delta x is approaching 0. So here, h is actually that delta x. That change in x, the distance between x and a, and we're looking as it goes to 0. And this f of x plus h minus f of x, that's looking at the change in y. So we're still looking at how our outputs, our dependent variable, is changing with respect to our inputs, our independent variable. And we've found a whole bunch of rules that we can use to find derivatives quickly, as opposed to using the definitions on the previous slide. And also, we found some ways to find derivatives for products, quotients, and composite functions, which can be really, really helpful. One rule that I'd like to point out in particular is the chain rule. So if you have the derivative of one function with another function inside of it, so it's a composite function, that'll be equal to the derivative of the outside function. So this is the derivative of the outside function, with the inside function still there, unchanged, times the derivative of the inside function. And one way to think of this is if you have the derivative with respect to x of g of f of x, we can think of it as a cloud. So we have g of something, and that'll be equal to g prime, with that something still there, times the derivative with respect to x of whatever that something is. So far, every derivative we've found has been for something called an explicit function. So if we just think about the general definition of explicit, it means stated clearly, in detail, leaving no room for confusion. For explicit functions, the dependent variable, which is usually y, can be written explicitly, so clearly with no room for confusion, in terms of the independent variable, which is frequently x. So we have y is equal to f of x, and y is defined explicitly as a function of x, which basically just means we're solved for y. So y's, all of them, just one of them, is on that side of the equation. And y is equal to whatever's on the other side of the equation. We know exactly what y is. It's explicit. What's interesting is we can also find the derivatives of something called implicit functions. So just like the dictionary definition of implicit is implied, though not plainly expressed. So for implicit functions, the relationship between the dependent and independent variable is implied. We don't know exactly what y is equal to, but we know the relationship between y and other pieces, usually our input, x, and we can kind of figure it out. So sometimes implicit functions can be solved for y, and we can turn them into explicit functions. So this would be y is equal to plus or minus the square root of 9 minus x squared. And we can kind of see that this looks a bit more complicated actually. And if we were to have to take the derivative, we'd have to split this up into like a piecewise function, which would be a bit of a mess. So it can be solved, but we're not sure that it actually helps us out. And some implicit functions actually can't be solved for y. So if you have something like sine of y is equal to y plus x, that gets a little bit tricky. So let's look at how we get the method for implicit differentiation. So even if it's defined implicitly, y is still a function of x. So we still have y is equal to f of x, we're just not really sure what that f of x is. But since it's defined as a function of x, we can use chain rule to find the derivative with respect to x of a function that's written in terms of y. Because if we have the derivative with respect to x of g of y, so a function where we have like y, it could even just be something like y squared. That will be equal to the derivative with respect to x of g of, well, y is equal to f of x. So this will be g of f of x. Just because y is equal to f of x, so we can substitute f of x in for y. And now we have chain rule. We have the derivative of a function with another function inside of it. So it'll be the derivative of the outside function g with the inside function f of x unchanged inside still, times the derivative of the inside function, so the derivative of f of x, which is f prime of x. So this is just using chain rule. And then we can look at this again and go, well, f of x, that's just y. So we have g prime of y, and f prime of x, that's just the derivative of y with respect to x. So this is just rewriting it since y is equal to f of x. And f prime of x is equal to dy dx. Now, we don't usually use all of that notation when we're differentiating implicitly, but it's important to know that it comes from chain rule, And that means that we basically differentiate using the same rules as we usually do, but instead we have a y, and we need to multiply by dy dx, which comes from that derivative of that y, so the derivative of the inside function from chain rule. So let's take a look at an example. We want to find dy dx if x squared plus y squared is equal to 9. So that means that we're taking the derivative with respect to x, d dx, of this x squared plus y squared, and that'll be equal to the derivative with respect to x of 9. So we can actually kind of distribute this d dx. So we have the derivative with respect to x of x squared plus the derivative with respect to x of y squared. And that'll be equal to the derivative with respect to x of 9. The derivative of a constant is 0. Now, we know the derivative with respect to x of x squared. That will be equal to 2x, just using our power rule. We have to be a little more careful with the derivative with respect to x of y squared. We still have an outside function of squaring, but now we have this y inside that squaring function. So we take the derivative of the squaring function, which will give us this 2 up front, and we still have a y inside of the function. And then we have to multiply by the derivative of y, so the derivative of the inside function, which will be dy dx. And this is still equal to 0. We're trying to find dy dx, which means we need to solve for this dy dx. So we can start just by making it so that terms that have a dy dx are all on one side, and everything else is on the other side, which we used to do when we were solving for x as well. But now we're just solving for this complicated looking piece, which just means the derivative. So we'll subtract 2x from both sides. So we have 2y dy dx is equal to negative 2x. We're getting there. Now this is a 2y times a dy dx, so we'll divide both sides by 2y. So we have dy dx is equal to negative 2x over 2y. And now we've solved for our dy dx. All we have to do is some simplification. So our 2's will divide out, and we have that dy dx, the derivative of y with respect to x, is equal to negative x over y. And that is the basics of implicit differentiation. Essentially, you differentiate and then solve for dy dx. So you just have to remember that when you take the derivative of y with respect to x, you have to multiply by that dy dx due to chain rule.